Maybe I'm wasting my time. Maybe this is a futile gesture, but I feel I need to do this. I was taking a walk and I got this idea in my head because I've been saying on various YouTube videos and whatnot, that money, prana, um, energy, electrical energy, or energy in general are all one. So I thought to myself, well, wait a minute. How would we turn a free energy circuit into a commercial description so that money is commonplace. Most people understand the basics of money. If they're an adult and they've done transactions like mortgages or whatever, buying a house or something. So how would we convert the behavior of the synthesis of electricity into something that we understand in the real world? Now we know the Federal Reserve creates fiat currency out of thin air, and nobody says they violate the laws of physics. Maybe because we have the IRS pouncing on people who don't pay taxes because the IRS is busy taking some of that excess currency out of circulation, but they're not the only dudes who do that. Golf courses do it too, oddly enough, and so do traffic cops issuing traffic citations. So there are a lot of different ways and means of taking money out of circulation, but we're still left with inflation and no promise to pay the debt that we incur in the creation of that fiat currency. Just we create it, and that's it. Now, free energy, I've never heard of anybody saying there's a debt, because most of the time all we hear about is, oh, it's not possible, defies the laws of physics, but nobody says anything about, well, if it is, doesn't that incur a debt that you have to pay back later? And some people have ventured to guess that it does, that we're stealing from the future or something, and we got to pay back sometime in the future. But as I know it, reactive power, which is all free energy is anyway, which is not usable in its raw form anyway, you have to convert it into usable power. Reactive power, you give back at the end of each AC cycle, which in Europe happens roughly, if I can 100 times a second. It's every 10 milliseconds, and for us, it's a little bit more than that, or less actually. Yeah, less. Anyway, not 100 milliseconds. No, 10 milliseconds. Yeah, is that what I said? Oh, I see. 10. Huh? No, wait a minute. 50. No, that would be 20, wouldn't it? Right. Every 20 milliseconds we give it back if we're in Europe, and every 20 milliseconds we get a chance to borrow reactive power. To energize a coil is usually the excuse given for why we could benefit from the use of reactive power, but certainly no other purpose, yada yada yada. And in America a little more frequently than every 20 milliseconds. But be that as it may, we're giving it back frequently. That's the point. And we're borrowing it frequently, and we have to renew the borrowing frequently. But in a free energy circuit, it's accumulating because it can't spend, because it's a wave in which the current and the voltage have been separated, causing the current to reverse direction. So what does that mean? That means you've got a credit line, basically. Instead of spending money, you're getting money. You're getting a credit increase. Your credit line keeps increasing. It keeps accumulating, according to what this circuit does. That's what I'm inferring. So you get this, you start off, it costs you something. It always costs you something. And the cost is 3 volts from a 20,000 cycle per second sine wave generator. So we have our own frequency here, and it's not 60 cycles per second or 50 cycles per second, because that's too slow to be of any use. You would spend it before you could possibly synthesize any. Or, to put it another way, if you could create the amount, it is possible to create the amount you need on any frequency of production. The problem is it becomes difficult to sustain or maintain a free energy circuit at lower frequencies, because either it goes comatose, which is most people's experience. That's why they say it's impossible, free energy does not exist. defies the laws of physics and any other excuse they can think of. Your mama don't approve. Um, or your wife, depending on who's mama in the family. Or it explodes. But in order to maintain it, you have to, and regulate it and turn it into a form that's utilizable, you have to raise the frequency. And I choose 20,000 hertz in this particular circuit only because it's convenient through simulation. You know, any frequency would work, in theory. 1 cycle per second, a gazillion cycles. It doesn't matter. What matters is what are you trying to do, and how convenient is it to do it, yada yada. All those little stipulations. That's really the only reason for changing the frequency. And I only need one frequency, because I'm taking reactive power, I'm borrowing it at the start of each cycle, AC cycle, and I'm returning it during the second half. So I borrow it during the first half of the cycle, and I return it on the second half. So I constantly have to renew my credit line, because it expires very quickly at 20,000 times a second. I can't go, the simulator won't let me go beyond 1.35 megahertz. And anything slower than 20,000 or 16,000 something I've gone as low as, the computer resources just can't handle it. It's just too slow. I'd need a supercomputer to use a 60 cycle, a 60 cycle frequency, such as we use in our electric grid. It just is impossible to work with. And the other problem is how much, in order to create the amount of it, like I said before, the amount of energy you'd have to create at a lower frequency, it would be so explosive you couldn't handle it. So at a higher frequency, you can create smaller amounts and spend them more frequently. See, everything's per unit time. You know, how many watts per unit time do you need? It's up to you. You specify the criteria upon which you want to base your free energy circuit, and then you match your criteria. So my criteria was always my electric car that's not running, only because its batteries are dead. Otherwise, it's in running condition. If you want to spend thousands of dollars on my behalf so I can convert to lithium, be my guest. But I'd never want to spend my money to do that. I do this instead. I'm a dreamer. I plan for a way to reduce my battery pack to just one battery. Everybody has it, even in gasoline cars. It's under the hood. And get rid of the battery pack that weighs 1,100 pounds underneath the bottom of my car and fill it with sand or lead or something, you know. Who needs it? We don't need it. So one 12-volt battery is all you need to run an electric car, basically. And so, but what frequency? So that's up to you. That's, it has to do with managing. What can you manage? So you set the frequency based on what you can manage. Because ultimately it all comes down to RMS, which is an averaging of your surges. Because to me, I've never seen it happen otherwise, so I don't know, but to me, the only kind of free energy I've ever been able to create are explosions of energy. I like to call them surges. But they're hyperbolic, and they can be quite explosive in some cases. That's why I don't use what I like to call Bewley's archetype, because it's too not manageable. It's so explosive. But boy, is it efficient at creating free energy. And the uttermost simplicity of design, even simpler than this. That's why I liked it so much, but I can't use it. And I could even run it in Paul Falstad's simulator, and I've done plenty of those simulations, but I can't use it. That was last year. This year's model is this particular circuit. So we get a credit line for reactive power every half cycle, and then we return it every half cycle. But because it's a standing wave, it doesn't really go away, and here's why. So there's certain rules to this commerce that are quite elegant, and one is escrow. Escrow is magnetism, and so let's focus on this solenoid core to these 5 coils over here. This magenta coil here, the transfer coil, represents what's really located over here, because for simplicity purposes, layout, formatting of my schematic, I put it over here. But in actuality, the coil is positioned somewhere over here. And how I arrange these are arbitrary as far as I'm concerned, because I don't know. The simulator can't tell the difference. In the real world, you will see a difference. I can bet that $100 right off the bat. So, and maybe this is not a cylindrical, linear arrangement. Maybe it should be toroidal. I would suspect toroidal is the most efficient, but I can't draw it very good. Well, I don't know. I could draw it, but I could redraw this schematic. But heads up, don't do it this way. Don't do what I do. Don't do what I say. What we have is escrow, and that's magnetic remnants inside our core here and the core here, but we don't have to get to that yet, so let's leave that alone. So we have escrow over here, and escrow is really bizarre over here because unlike, okay, now we're over here. Escrow over here charges us for our use because only now do we get to use the energy. So they're going to charge us. It makes sense, and that's called hysteresis. Over here, we don't use it, so they don't charge us. So we could say that this is the conversion of cryptocurrency over here into solid silver-backed or gold-backed, if you prefer, currency. You redeem your cryptocurrency and you get specie. You get gold or silver specie. That's the technical term for the physical object is the specie. But over here you've got cryptocurrency and you're building it up in your crypto bank. The Bank of Vinny cryptocurrency. And you start off by pumping it real specie in the form of 3 volts rated at 20 cycles per second. So the sine wave generator, and yet that's the voltage though. Maybe we better step back a bit. Now what is voltage versus current? Well, voltage is the actual specie count. 3 ounces of pure silver, 3 troy ounces of silver, let's say, is 3 volts. So let's make 1 troy ounce of silver equivalent, in Mike Vinny's cryptocurrency bank here, let's make it equivalent to 1 volt in the microcap simulation of this circuit. So 1 volt is equal to 1 troy ounce of pure 4/9 fine silver in my little cryptocurrency money machine. It's going to churn out money, all we want to spend. And now the amperage, the current, as I've said, or I imply, over here, derived from 100 nanowatts. It's actually slightly less than 80 nanowatts, but I just rounded up to 100 because I didn't have time. I didn't want to take the time. I didn't have the patience to take the time to run the simulation long enough to see where it plateaus. So I took a guess estimate that it's something less than 100 nanowatts, and I'm pretty sure it is less than 100. So, but if we just say it's 100 nanowatts, you divide by 3 volts, and you get something like 30 amps is what you're draining here. Now the amps is the actual exchange rate per unit time. We have to always keep specifying, even though the simulator may not make it obvious, but it does, because when you do the run, when you run this, you do it for a certain length of time, and you see what happens. So current is the movement, the exchange rate, not the exchange rate the way we normally think of. I'm using it in a different context. Okay, so I shouldn't use the word exchange rate. It's actually called the velocity. So current is the velocity of monetary exchange. And to a fiat currency, that gives it value. The Federal Reserve likes to say, well, it's not backed up by any gold or silver, but it's backed up by your belief in your federal government, which is a bunch of hooey. It has nothing to do with federal government. It has to do with your usage. You don't have to believe in it. You could care less. Anybody could care less. All you have to do is use it. If you don't use it, they translate that into their coded message. Oh, you believe in it. Who cares? I use it only because I have to. I don't believe in it. Or else I wouldn't be promoting the Liberty Dollar 10 years ago, 11 years ago in L.A. I spent thousands of my silver Liberty Dollars into circulation to pay bills and buy food from Whole Foods and whatnot. So obviously I believe in something other than the fiat currency, so I don't have to believe in it in order to use it. But it's only the use of it that puts value behind it, because if you stop using it, the value of the dollar goes to zero. If everybody collectively stops using the United States dollar, its value goes to zero, and that's I'm speculating now, probably the only reason why Donald Trump, our United States president, has proclaimed the United States dollar better than cryptocurrency, more stable, and he's bad-mouthing cryptocurrency because he's being told to say that. Because any currency gains value based on its speed of transaction. You know, how many dollars, or how many units, shall I say, how many units of that currency per unit time undergoes an exchange between one party and another. That will help contribute to the value of that currency in the eyes of its users, not to anybody else. So if you just put cryptocurrency in your bank and never spend it, it really does. It's like any other fiat currency, unless it's backed by gold and silver that you can redeem. You know, something tangible, or fungible, maybe is the technical term they use. But be that as it may, we call it tangible, so I'll stick with that. Actual. Now here, it's in terms of what use we get out of it: heat, light, rotate a motor shaft. And then over here is the cryptocurrency that you can't get use out of, and its reactive power. Now, so I have to have. Now, so how do we translate this? I'm trying to think this out loud, because I didn't work this out completely when I was taking my walk. But let's say I've got 3 troy ounces of pure silver in my little that I possess. But I don't know if that'll work. So let's just run on that assumption and see how it goes. Now, nano is quite a small unit. We know if we use 1 ohm resistor, we get on a 1 volt battery, we will get 1 amp of current. So I'm assuming now that if a resistor being a regulator of the flow rate, if I use a 1 ohm resistor on a 1 volt battery, then I'm spending 1 troy ounce of silver per unit time. That's what's going to happen. But since I have 3 volts, I'll be spending 3, but I only have 3 to begin with. I don't get to replenish it yet. Now in the simulator, it just keeps coming as if it's an infinite source. But I'm only using nano. I'm using a tiny portion. And if my little 3 volt battery has only 3 amp hours in it, I can run my little virtual experiment for quite some time before I run out of money in the bank. So it actually does point to a physical. The analogy is working quite well here so far. I've just never thought it through like this to see, okay, what does the simulation mean in the real world, in the real context in which you and I live and breathe, not the world of the simulator. So, not only to help you understand, but me as well, because I have a hard time understanding this. So I got 3 troy ounces of silver in my wallet or my bank account, and I only need to spend a portion of it. And so what I do is I take it to my cryptocurrency bank and I convert it into cryptocurrency. So now we can divide it into any size unit we like to spend any size. And I'm going to have to, because I'm only going to be spending teensy-weensy little nanoamps of it per unit time anyway, or less. 20,000 cycles per second, it's going to be even less than nano. 20,000 times less, to be more precise, I would imagine. Right off the top of my head without trying to be accurate. So I'm going to be spending little, God, it's not even like a grain of gold. or a carat. It's more like a few molecules, I would imagine, or maybe a few hundred molecules of silver that I'm going to be spending per unit of time in order to fund my little cryptocurrency exchange here to build up reactive power to the point that I'm spending out here more than I'm feeding it over here. That's the goal here, is to figure out what it would actually mean in the real world. So far I got 3 ounces of silver, and I'm spending it at a very slow rate because current is going to be my rate of exchange. Voltage is how much I have in the bank to spend. How much in my wallet, my cryptocurrency wallet, do I have to spend? Yeah, I better stick with cryptocurrency wallet, crypto wallet, or just plain wallet. Now, in the course of manufacturing, the amplification of my wallet, which is what I'm doing, right? I'm going to amplify my wallet without having to do any trading online. I do it in-house, unless I have to do it online and form a little house of traders such that we've figured out with software how to do all this between each other over the internet so that we can have an output that we can all share and divide among each other, or just have available in a cooperative bank account, so to speak, or a cooperative wallet, a co-op wallet, a co-op wallet that we all participate in, so that we have more outcome than what we individually had put in the beginning, if we have to trade with each other in order to make this happen, and not merely trade with ourselves. I guess you call it inside trading. There are rules against that. Yeah, well, whatever. But what do you think free energy is? It's in-house trading. So, I've got 3 ounces of silver I have to put in the kitty, in the pot, in the center of the table. You know, we're going to play cards or something. And we convert that into cryptocurrency. And then we start dividing it up into smaller portions and feed it into our system. So what are we going to do with it now that we feed it into the system? We're going to pass it through the first 2 things we want to pass it through of any significance are the 2 voltage coils. They're going to turn it into a magnetic field based on the mass of the copper winding, you know? The size of the wire, the number of turns, the diameter of the turns. All that equates into mass, and Joseph Newman kicks into gear here. The ghost of Joseph Newman, the spirit of Joseph Newman, kicks into gear here because it's totally relevant. Whatever he said about the mass of copper, you know, it's true. Well, whether or not, you know, we got to worry about something trivial like a little gyroscopic top spinning around, to me, I could care less. But the mass of copper, if you read his book, the beginning chapters, the opening chapters, when he talks about the mass of copper, he has some very interesting illustrations that he conferred with a physics professor, I believe, back east somewhere. And it makes so much sense, you know, if you take 2 different coils, same resistance, but they're vastly different gauge, wire size. And so they're going to have different mass, but also different inductances, which means you're going to get a whole lot more power out of one than the other, even though their resistance is the same. In other words, what's it going to cost you? The bottom line. Because the resistance is going to be equal, but anything else is not equal. And the outcome is not equal, and that's his rationalization for making such a humongous coil to his device. Even though the resistance was so teensy, he didn't need current to run his motor. All he needed was copper and lots of it, which is the way he explained it. And it's a nice way to explain it, even though it's not the whole picture. It still is a nice way to explain it because it's the bottom line. Now, he's got to put the money up front to pay for that copper, but that's a one-time investment. And it's not like you consume the copper like you would a log in a fireplace, so I'd say that's a pretty good investment. Well, it works here because the size of the VC1 and VC2 matter. Okay, so we've got an exchange system going on in here, and it's a step-down transformer because the current coils are really teensy, and they are, we have 4 warehouses basically, and the two CC coils, the two current coils store current, while the two voltage coils store voltage. Now what does that mean? That means the voltage coils are amassing crypto silver tokens. All right? I feed it a certain amount, but they accumulate it. While the current coils, I guess, would be the bookies. They, let's see, they would record the transactions, but they're not really the bookies. They're more like the retailers, the merchants at the front end, you know, transactions. So I guess what you have to do here is you have to set up artificial transactions in which you buy and sell meaningless virtual products and services that don't exist. And they have to be rated, you know, how many dollars or how many units of currency per transaction. And it's because the current coils are going to be focusing on maintaining a certain exchange rate of commerce. So in a sense, this is kind of like a microcosm of the economy when you think about it. And yet it's regulated in such a way as to build the economy, but in the end, not inflate the quantity of units of currency such that each unit becomes devalued. You know, that's what inflation is. Instead, at the end, we want to be able to convert it so that the units coming out are equal to the units going in, the value per unit, so that the total value is greater because we're going to have more units coming out rather than the units going in. So I guess what the current coils are represents commerce and the rate of exchange, the what did I call it before, the velocity. The velocity, the exchange velocity, not the exchange rate, but the exchange velocity. There we go, the exchange velocity. While the VC1 and the VC2 are your checking account. You know, it's a temporary, it's not a savings account. In a sense, this sine wave generator is feeding off of a 12-volt battery that gives it 12 volts and then it outputs 3 volts. In a sense, the 12-volt battery feeding this sine wave generator, it's implied, it's not here in the schematic, would be your silver mine. You know, it gives you the silver raw from the earth, 12 volts of it. And you lose 7 volts, which is highly not efficient. You lose 9 volts, actually, excuse me. You lose 9 volts in the course of putting out 3. You lose 9 troy ounces of silver. So you're paying a lot to the mining company. Let's say, you know, some Vinny's mining company up in the Ozarks or something. But you only pay once, because you're going to be putting out so much out here, no one's going to care, you know, that you lost so much initially. The tears spent here in the loss of 9 troy ounces of pure silver is not something to really cry for more than a microsecond, because it's not going to concern you for more than that anyway. All right, so we've covered, so we have these checking accounts here storing up crypto units of silver, and then we have a place to spend them and notice here it's a closed loop. We spend it back to ourselves. So it is not only in-house trading, it's in-self trading. You trade to yourself. And there's hardly any resistance, inductive resistance, so it's not a whole lot of, in these coils, not a whole lot of training. These are, so actually, these are teeny-weeny transactions, so small, you couldn't even relate it to the real world. It's so small. A tiny fraction, 2 microhenries, you know, how much is it going to spend per unit time? So little. Yet it's vitally important, because it's the rate of exchange, not the size of each exchange. When I say exchange, now I mean buy and sell, the trade. It's the frequency of the trade, not the size of the trade, that will matter in the CC coils. While in the voltage coils, it's the opposite. They're going to harbor a lot of voltage. See, the CC coils have absolutely no voltage, so they're totally liquid assets. while the voltage coils have a certain amount of liquidity, but they're mostly tangible. And their trading is slow, far slower than the current coils, but very big. So we're talking gazillion barrels of crude oil kind of, between countries, in the voltage, these two voltage coils. Now the transfer coil over here gets to bleed off a little bit of what goes on in here. And it gets transferred to it, but very little because it's 10% coupling. So it's like the broker or the bookie or the whatever you want to call it, who makes all of this possible, and he wants to take a 10% cut. And so he takes it, a 10% cut. And everybody else is happy with their 90% shared among themselves. I mean, it goes nowhere. Now, the voltage coils, they have to share it, but how much are they going to share? Because they're dominantly voltage, just like a Joseph Newman motor. So they share very little with the rest of the circuit. And so everything is cool. Everything's nice and efficient. And anything that is shared to any great degree stays with the person who has it. And it's transferred from these by way of magnetic induction. So in a sense, you could say it's borrowed, because it's all along this line. These 4 accounts, or 5 accounts, these 4 accounts, these solenoid 4 accounts are all borrowing and sharing. They have a pooled asset. It's only the transfer coil that's going to lose some, because ultimately that's going to bleed it off going out this way. And the voltage coils, you can imagine, would lose some too, because they go out to here and then go out there. So ultimately, all these coils lose something, but they're geared to lose very little per unit time and build up more than they lose. Now, all of that is relative, so you have to make sure you function this circuit within its limitations, because if you spend more than it can produce per unit time, synthesize, if you prefer over the word produce, then of course the whole thing will collapse. And then you just have to build a bigger circuit with bigger voltage coils, VC1 and VC2, so that the contrast between the VC coils and the CC coils is greater rather than less. Let's see, what else can I say here? So the magnetic core is kind of like escrow, I guess, because it remembers everything. So it's the bookie. So actually, the transfer coil is the broker, but the solenoid core is the bookie, the accountant. And he doesn't cost you anything down here. The transformer, the core, will. He'll take a siphon off a little, in terms of hysteresis loss, and charge you for being able to convert this reactive power into usable inductive power. And the same thing goes here. You're gonna lose a certain amount of specie because, I'm getting ahead of myself. You always lose something when you want to do conversions, right? Okay. Let's see. But the core here doesn't lose technically, because there's no hysteresis technically in terms of the simulation. So this is not a transformer core. It's a solenoid core. It's iron rebar, or something, welding rod or something. It's a solid iron core, and so you're not going to have loss, and so you're able to communicate, but it has to remember what goes on in all these other coils. So it has to be imprintable and also remember and retain a memory of what has happened and not forget. It has to remember. It has to have perfect memory. But it's not costing you anything. Now, let's see what else. Now, the diodes here are going to force all of the transactions onto the top side of this transformer down here and empty out the bottom side and keep it that way. Now, I found in the past that you might have to invert this capacitor once in a while because of one side getting all the storage and the other side not, because eventually what might happen, and this circuit may not be perfectly stable, the regulation built in here fails you, and it fails gradually. At first you don't notice it, but I've never ran the simulation long enough to find out what happens if you run this thing for an hour of actual time. I only know what happens if you run it for 10 seconds actual time, in terms of what the simulator tells me. Maybe hours in my time, but as far as the simulator is concerned, it's like 10 seconds. And in some instances, the thing started to escalate all over again. So you might have to just swap the connections, turn this capacitor around so that it discharges itself and then goes, and the cycle starts all over again. So you might have a little pause, when you rotate this capacitor. So it's going to... Oh, I have to stop. Sorry, I have to stop this videotaping session temporarily. Sorry. To be continued.